All right. Hello. Welcome, everyone. Thanks for joining us today. Today we have Professor Vinitsky from NYU Tandon, based in civil engineering, with a PhD in control from UC Berkeley, with Professor Alexander Ben. His research goal is to see complex human-like behavior emerge from unsupervised interaction between group of learning agents with applications focused on robotics and transportation. He's really interested in pushing the state of the art in multi-agent RL algorithms, also in designing new data-driven simulators and trying to deploy simulated designed controllers into real-world systems. He has worked at Apple, Tesla, DeepMind, and Facebook AI Research in the past. He's also a recipient of an NSF fellowship. All right, so the floor is all yours. You can get started, Professor
Okay,
Levinsky.
cool. Well, thank you all so much for having me and for inviting me. Yeah, as mentioned, this talk is titled Robust Autonomy Emerges from Self-Play. I'm happy to take interruptions. I can make up pieces of this talk faster or shorter as needed. So, but I can't see. So if somebody can monitor the chat, if somebody has a pressing question, I'm happy to answer it. This talk is titled Robust Autonomy Emerges from Self-Play. And one of the kind of research goals of my career, and maybe one of the kind of blue sky ideas of the field of multi-agent learning, was this idea that we could build kind of rich simulated worlds, drop a bunch of agents into them, have them interact with each other, and have the thing that come out be broadly intelligent in some way. And I think this is work, not to overhype it, is one of the first instances of this kind of vision working for actually designing a capable system. And so, to kind of get into it, we kind of have one way that we know of to build human level bots, or like human level agents in any domain. There's really, LLMs are extremely impressive and extremely useful, but they're not, quite at human level capability. But there is one setting in which we build agents or bots that are at human level capability and exceed it. And the specific setting is zero-sum games. And in these settings, almost exclusively, these are all built using some kind of self-play reinforcement learning method. And if you don't know what self-play is, I'm going to get into it in a little bit. But the idea is you're going to set up two bots. They're going to play against each other. One of them will get a little better, which causes the other one to get a little better. And you get this kind of ratchet effect where they're going to get progressively better and better and better. And this is how we've built kind of human level StarCraft, superhuman Dota, superhuman Go, superhuman chess, the exception being poker, which is built through a totally different set of techniques. And the question that has kind of motivated this work for me is like, why can we build superhuman bots with RL? But not self-driving cars or robots or any system that has to interact with humans? And there are a lot of practical, technical reasons why this is the case. And I'm going to get into those a little bit. But this is kind of was an underlying motivation for me for a long time. And the answer, I think, is that actually maybe we can. Maybe there is a way to bring these techniques to the design of robotic systems that have to operate in mixed settings with humans. So there are three results I'm going to talk about. So first, I'm going to talk about how we design a simulated, potentially human-level self-driving car. This is in simulation, and our ability to test whether something is human-level in simulation is limited, so there's going to be some serious limitations on what we can say, short of putting it to a physical car. But I think there's some really exciting, compelling results here. Two, I'm going to describe how we designed a simulator that can generate millions of hours of driving data per hour, allowing us to really scale up reinforcement learning and see what its limits are at the trillion sample scale. Three, what I think is a surprising demonstration that you can build robust planning agents into a tiny, like absolutely tiny end-to-end neural network. So that's kind of what I'm going to go over. Or in short, how to build an autonomous car with no human data, entirely through self-play. So we're going to first talk about end-to-end planners with minimal or no human data. Then we're going to move into the technical approaches we use to scale up self-play. And I'm going to end by talking about what I think are some surprising observations about what happens when you scale RL up and why it's kind of worth doing so and investing the time to do so. The content of this talk is a paper that we put on the archive about 4 or 5 months ago called Robust Autonomy Emerges from Self-Play. I want to spend more time on this title slide than I would normally spend on a title slide because this work is the product of equal collaboration between the 8 authors listed here with a star, and then Taylor Killian, who popped on for a last-minute assist, and then led by Stuart Bowers, Ozone Center, Philip Crown-Buell, Lachlan Colton. So this project was like totally equal co-work between myself, Marco, David, Alex, Rohi, Alexei, and Eric. And since not many projects have this form, I wanted to kind of stay here and point this out, that I get to talk about it here today, but this is equal work from all the folks here. So that being said, what is this paper about? It is about building a robust multi-agent planner entirely from self-play. And to provide some context about why that's interesting, it's useful to think about what the stack of a self-driving car is. So the way most self-driving cars are built is they have some perception pipeline. So something that, takes in cameras, LiDAR, radar data, and converts it into a set of often bounding boxes or voxels describing where everything in the scene is, what is drivable, what is not drivable, and things like that. That this pipeline is breaking down a little bit, but we'll talk about that in a second. These bounding boxes or perceptual outputs are fed into a prediction system. That prediction system predicts where everything in the scene is going to move, where the pedestrians are going to go, where the cars are going to go, how fast they're going to go. And it's usually multimodal. It'll generate a set of predictions. This set of predictions is fed into a planning module. That planning module will generate a set of trajectories that seem reasonable and compatible with the predictions. And it'll also generate some costs over those trajectories, saying like, oh, this one feels more safe, this one feels less safe. And then there'll be some module that helps select out from those trajectories which one is probably the best one to start taking. And we'll start moving along that trajectory with some controller that helps us follow the trajectory that's been selected. And then we'll just rerun this loop somewhere between 10 and 100 times every second. And what we're going to talk about here today is something that we think can subsume this part of the stack, that can, given perceptual outputs, can kind of end-to-end do prediction, planning, control. We don't have any explicit such modules. It takes perceptual outputs, inputs, and outputs controls. And we're going to do this in a fully human data-free, end-to-end way. I think this is the first time there's been like a serious candidate that could plausibly subsume this stack. But one thing I also want to add is that what this is going to turn into is an RL agent that generalizes zero shot. So we're going to train with no human data, and then we're going to test it in domains where it's never seen the agents that it's interacting with before. And despite that, it's going to generalize and be extremely robust in those domains, which I think is also an interesting property that is sometimes hard to get into RL systems. So there's a couple of things in here that I think are exciting. By the way, y'all can hear me? Everything good?
Yes.
Okay, great. Awesome. Sorry. I don't see the
I
screen.
think there is a question.
Great.
And you can ask.
Yeah, just chime in and ask.
I think he just clicked. Probably it's fine. Sorry, go on. Sorry.
Okay, sorry. Yeah, I can't see the chat. So if there is a question, I can't. Let's see. Aha. Okay. Misclick. Got it. Okay. Okay. So why would you want to do this? If you go to San Francisco, you will see self-driving cars driving around. There's no human in there. There's some amount of teleoperations, so people do occasionally have to check in to like make some decisions for the car. But it's mostly driving free. And how are these systems built in contrast to the way that I'm about to suggest that we do it? So increasingly, companies are chasing self-driving through something that looks like this pipeline, with some appropriate caveats. So first you have some kind of diverse data modality. So, maybe if you're Tesla or increasingly other companies will put cameras on their cars and drive them around, you'll collect billions and billions of miles of humans driving around. You'll take all that data and feed it into some big model and do a supervised imitation learning models. So you're going to just try to predict the actions that the humans do. There'll often be something on top of that, like some kind of filtering procedure where you filter out bad data or bad drivers, and you could kind of interpret that as a type of offline RL, like top 10% filtered behavior cloning. And then out of that, hopefully you can follow this like standard ML pipeline. And as you scale up the size of your data set, your loss keeps ticking down, and the thing that gets better and better. And if you're a company like Tesla, this honestly has been working reasonably well. Not to the level of being able to deploy a self-driving taxi, but to the level where people can take their hands off the wheel for somewhere between 500 and 5,000 miles, which is kind of shocking. So that's something you can get. And just to contrast that, maybe a company like Waymo will have more of a segmented stack that's a little less end-to-end and has a little bit more human design in the loop. But this is kind of the just as in robotics, kind of a dominant trend in the field is imitate human data. And this works pretty well. So one might say, like, why would you want to be human data free? There's a couple of reasons. First, for me personally, I'm interested in superhuman performance, not human level performance. Humans crash every 20,000 to every 100,000 miles. They have a fatality every roughly 100 million miles. That's in the United States. I don't know the numbers outside the United States. I think they're roughly about 5x higher in India. And that's the only other country for which I know the numbers. And if you're going to do pure imitation learning, you're going to cap out at the level of roughly the top 10% drivers in your data set. And I really want to build a world where we have no collisions at all. Collisions are like the fourth leading cause of death, fifth leading cause of death, something like that. What if we just crash never? How do we do that on top of imitation learning? Probably at some point if we're going to have to do RL on top of it. So might as well start doing RL now. 2, we're not all Tesla. We don't all have billions of miles of human data to work with. So, there's that too. 3, just from the perspective of my research group and what we're excited about, we want to scale design capabilities, right? It's exciting to think that, maybe a small team could design a self-driving car. And if a small team could design a self-driving car, then what else could we design if that were true, right? Maybe there's all sorts of other autonomous systems that suddenly become accessible, and we see a proliferation of autonomy in ways that aren't possible when every effort goes through 1,000 to 2,000 person company. Obviously, the hardware will always be a bottleneck here. So putting that aside, how do we build the system? Assuming that motivation is valid and interesting, how are we going to build a self-driving system? And there's a couple ideas that we kind of draw on from the multi-agent literature here and from the RL literature. The first is a scalable algorithm. So if you're not familiar with what self-play is, the idea of self-play is fairly straightforward. We have some policy pi sub t. We collect tons and tons of games in which policy pi sub t plays against itself. Tens of thousands of rollouts of pi t playing against itself. We take those rollouts and we put them into some black box training algorithm. In our case, it's going to be PPO, or proximal policy optimization. And that spits us out a new policy pi sub t plus 1 that we use to repeat this loop. And so kind of, looking inside that box, what's happening inside here from the perspective of every individual policy pi sub t is that we're running the standard RL loop over and over and over again. And, kind of to make that point salient, from if this is a driving simulator around here and we have some cars here, so like, this green car wants to get to its green goal, and this blue car wants to get to its blue goal over here. Every policy here is a copy of pi sub t. They're all acting totally decentralized. There's no joint decision making, but they all have a copy of roughly the same policy that running on board. So yeah, we do that. Our black box algorithm for the purposes of this paper are going to be proximal policy optimization, which for one reason or another has turned out to be quite a good algorithm for multi-agent games. Whereas, it's also quite a good algorithm in other settings. it turns out to also be true in multi-agent settings, which have some additional complexities that often cause people to go towards kind of more custom multi-agent purpose algorithms. We can talk a little bit about that at the end. So to revisit, this is how almost all human level bots are built. Taking self-play and some kind of RL algorithm, sticking them together, and then getting a human or superhuman level bot. StarCraft was built through AlphaStar, which is kind of self-play built on what's called a prioritized policy-based response oracles method. Dota was built on PBO, Go is built on AlphaGo, but they're all built on this self-play idea plus some algorithm used to implement self-play. So why don't we just build cars this way? Right? Like, why can we not just take these ideas that let us build superhuman bots in these games and build cars? And there's one very serious technical hurdle. And the serious technical hurdle is this. Driving, unlike these other games, is what's called a general sum game, whereas the games I've been referring to before are what are called zero sum games. So a zero sum game, and you could keep in mind poker, has a couple properties that are extremely pleasant and make life very easy for you. The first is that there's a known reward. We know how to win the game, right? We know what it means to win a game of poker. We don't have exactly such an equivalent notion of winning in driving. But it also turns out that for zero-sum games, there's a property wherein there is a particular strategy that you can play called like the policy corresponding to a Nash equilibrium. And if you play that policy, you are guaranteed to do well against every other policy that you could play. Doesn't matter who you play. It doesn't matter what strategy your partner takes on. You're going to at least get a draw as long as you play the strategy. And it turns out also that if you play that Nash equilibrium strategy, that strategy that's guaranteed to get a draw against the kind of perfect opponent, it decimates humans. It just blows humans out of the water. And driving does not have any of these properties. It's a general sum game. There's unknown reward, but and the best way to play is context dependent. It depends on who you're driving with, right? If I'm in the USA, I need to drive on the right hand side of the road, and if I'm in Singapore, I need to drive on the left hand side of the road. And sure, I can build some of that into the reward function, but there are other components that are also really challenging to build into the reward function. For example, if the other drivers around me have a certain reaction time, I have to be cognizant of that reaction time. If I don't reason about that reaction time, and I assume that everyone can react at the same speed that a self-driving car does, I'm going to get into problems where I rear end people because I assume they're going to react. So in these games, there isn't an obvious best way to play. There isn't an obvious reward. And so a common temptation, and a very reasonable temptation, is to use human data to alleviate this problem, right? We don't know exactly what the right way to play with humans is, so let's just imitate the way humans play. And it makes a lot of sense. What we're going to show is that, surprisingly, despite the fact that the best way to play is context dependent, you can find a strategy that works well across a lot of contexts. So works well with simulated self-play drivers, works well with all sorts of holdout drivers that people design, and then also works well when played against human data, despite the fact that there isn't necessarily one best way to play. And kind of, if there's an underlying logic to this, one way I often think about this is through this idea of what I sometimes call the simulation hypothesis. And the idea here is, we don't know exactly what world we live in. Imagine there are many, many parallel worlds. What we're going to do is we're going to build simulators that simulate many different possible types of worlds, of which the world that we actually live in is one. And if we have a policy that does well across all those diverse simulated worlds, then it's probably going to do quite well in the world that we actually live in. So the goal here is to inject a ton of diversity into training, and then either create a policy that is robust across all that diversity, or use a little bit of data online to identify which world we're actually in out of all the worlds that we could be in. And this idea is in some ways often implemented in robotics through this idea of domain randomization, where you're not totally certain about the friction and the mass of your robots, you just randomize it. And then at test time, you have a policy that is kind of robust across those values. Okay, so this is us, and here's all the other worlds we're going to simulate. Hopefully, if we do well across all of them, we're going to do well in the world that we actually live in. So how do we turn this into the design of a simulator? One perspective we adopt is to make train harder than test. Right? So we're going to fill our world with policies that are unpleasant to drive with. We're going to have cars that drive in the wrong lane. We're going to have cars that are kind of pushy. They go when it's not their turn. We're going to have cars that wait too long on a stop sign. So, you'll get to a stop sign and you'll be like, well, it's your turn to go, and it won't go. And it'll just wait. So you have to make a decision about whether they're going to go and whether you can just take over their turn for them. We're going to have cars that drive through red lights, right? So that you're always cognizant that you're never exactly safe, no matter where you are. And in the end, we're going to hope that the policy of humans are somewhere inside that diverse space of policies that we're generating. Or if it isn't, that we're at least going to be extremely robust to hold out policies because our training world has been so complicated and unpleasant. 2, that when we train in this diverse world, we're going to learn a lot of fundamental skills that are going to be extremely transferable, even if the world that we test in is not the same as our simulated world. So for example, and this is going to be the notation that we adopt throughout this talk, over here we have this little green pin, and the green pin is the goal. So anytime you see a green pin, it's the goal of some agent. And in this case, the blue car wants to get to this green pin, which is somewhere out on the map that we don't see. And as it's driving along, it's driving next to this orange car. And at some point, the orange car is going to swerve, which in turn causes the blue car to swerve. And if you're living in a diverse world where sometimes cars are unreasonable, don't think about you and kind of ignore you and just cut into your lane, well, you're always cognizant that you might need to swerve at any time. So you're going to generate your plan such that you can swerve if needed. And one way this sometimes shows up is, for example, if you're driving in the highway and you see that the other lanes around you are kind of empty, you're just going to keep a little more distance than you would have otherwise. And that distance keeping is going to be emergent from driving in a world where sometimes cars do aggressive cut-ins. You're also going to need to learn to reason about uncertainty in such a diverse world. So, for example, you never know exactly where the other actors are going to go. You don't necessarily know where they're going to yield to you either. So in this case, we have a blue car. The blue car wants to take a left because its goal is somewhere down there on the map. And it's driving with this orange car. And it doesn't know if the orange car intends to stop for it and yield, or whether it tends to shoot through and take priority. And so you need to learn to drive in such a way that both of these possibilities are maintained. And you need to reason about both possible goals at once. This is sometimes called contingency planning. So if they yield, you're going to go through, and if they push through, you need to be able to slow down enough that you can maneuver your trajectory to avoid a collision. And this fundamental uncertainty over the goals and intents of other actions is a very powerful prior. It means that you're forced to constantly reason about every other agent in the world. And I think this is a pretty powerful thing to build into a system. 3, you need to learn to reason about risk. So here's a case where the blue car wants to get to this its goal, which is on the bottom left, and the orange car in front of it just comes to a stop. To go around the orange car, you need to drive into the oncoming lane, and to make any progress to your goal. And to do that, you need to learn to do things like peek out and make sure that it's safe to do so. And you need to reason about whether the orange car is actually maybe going to start up again at some point. And so you need to constantly be reasoning about risk and what other agents are going to do. So there are a lot of really capable skills that are developed if you drive around for long enough in a diverse enough world. And this turns into 2 knobs, right? You can generate a lot of uncertainty in this world. You can generate a lot of diversity in this world, and these turn into controllable knobs on robustness. Basically, if you turn up the diversity a lot and you turn up the uncertainty a lot, well, then, you're never certain that it's safe to exit your driveway. Maybe you exit your driveway and a pedestrian runs as fast as they can and jumps in front of your car. Okay, you're maybe never going to go out. But you can kind of tune these knobs to create policies that are capable at handling some amount of uncertainty and diversity, but are still willing to drive. And the final ingredient into our system is a trillion steps of agent experience. You know, I'm not going to say that it's necessarily desirable to have to need a trillion steps of experience to build your RL policies, but it is going to be very interesting to see what happens at this scale. And you know, future work can work on getting that number down now that we've kind of demonstrated this proof of capability. Putting this all together, we have a system called Gigaflow. Gigaflow is an entirely GPU-driven simulator written in PyTorch. So everything in it is just pure PyTorch. And basically what we do in Gigaflow is we have an 8 GPU node, and on every node, we take a map from the simulator called Carla and place 4,800 copies of it on a GPU. So these maps are kind of like, they look a little bit like mini cities. They vary a lot in size. Some of them are about 400 meters in any given direction. Some of them are kilometers in any given direction. And they have things like clover leaves, roundabouts, U-turns, all sorts of stuff in them. They're very rich maps. And we only train on these 8 maps. So anything you see outside of this is just going to be like pure map generalization. So in each of these worlds, what we have is about 150 agents per world that are just going to be driving around constantly. Basically, we place the agents randomly over the map. We throw goals for them randomly all over the map, and then we just ask the agents to drive to those goals while generally avoiding collisions and, you know, optimizing some small reward function that we've written down. But the dominant components of what they want to do is they want to reach their goal, and they want to get there without colliding. If they collide, they get frozen, and their episode is over. What does this world look like from the perspective of any agent? Well, here we have this agent. It's the kind of darker blue car. It sees all the cars around it. So it sees, you know, these kind of big cars. It sees these narrow cars that are kind of intended to be cyclists. It sees these small pedestrians walking through. It sees the edges of the map, and it knows that it's not allowed to drive off those edges of the map. But it just sees a small local view around it. And then it also knows roughly where its goal is relative to its position. It doesn't have a direct route that tells it exactly how to get to its goal, but it does have like some rough guidance points. So because for the very large maps, you might need to drive like straight up a mile through some round, windy turns to get there. We put this all together, the road boundary, the lane points that represent the center lane, stop lines, which represent traffic lights, your own vehicle state, including your size and width, the position of the other agents, and some conditioning and goals. And I'll talk about what those conditioning goals are. And then we feed this into a small equivariant MLP and directly predict longitudinal and lateral jerks, which is kind of one step down from accelerations. Okay, putting this all together and training at scale, we generate 10,000 years of driving experience on our 8 GPU node. At any given time, we are simulating millions of drivers. And in total, we're constructing 1.6 billion kilometers of simulated driving. This whole system trains for somewhere between $1,000 and $7,000. This is just based on cloud compute cost estimates. We don't know what the actual cost of training the system was, but it runs on an 8 GPU node for about 10 days. You could think of this as a lot relative to the cost of collecting billions of kilometers of human data for training imitation learning systems. I think it's actually very little. And I'll talk at the end about some open source reproductions of it that we've been working on to make this accessible to everyone. But putting that all together, if one other way to think about the $7,000 cost is that once you have your agent, you have your simulator, it costs about $5 to generate 1 million kilometers of simulated driving data, which is, you know, you could think of this as quite cheap. Just as a fun thing, this 1.6 billion kilometers is roughly the distance between the sun and Saturn. And if we compare this to the amount of open source publicly available driving data, there's in total about 0.1 million kilometers of data between all the data released by companies like Argoverse, Argo, Waymo, Newplan, and then there's some human driving data in a simulator called Carla. So orders of magnitude, our agents are trained on orders of magnitude more data than is available through public data sets. So I mentioned it's really important to generate diversity in this world. And so I want to tell you about this kind of cool trick we use to generate that diversity, which is I haven't seen used all that much, and I think is a really nice way to do this. The trick we do is called randomized reward conditioning. And it's kind of an obvious trick. What's surprising is that it works. So we have a bunch of different reward terms. So we have reward terms like center bias, which is like how much do you want to stay in the center of your lane, or do you want to drift left or drift right, or even drift into the oncoming lane? We have terms like goal rewards, which reward how urgently we want to get to our goal, right? Whether get a big bonus or a little bonus. We have terms for lane centering. So how much do we care about being like kind of, centered in the lane itself? We have comfort terms for how jerkily you drive, like how much you wiggle your steering wheel quickly. And then we have some other terms for how the heading of your car is aligned with the lane and things like that. And for each of these reward terms, they're parameterized by a weight alpha. And what we do for each agent is we draw a value of alpha for each reward component from a distribution, and then we provide the weights of those alpha weights as input to the neural network. And so every agent has a different randomized reward function, but it knows what the weights of that randomized reward function are. So you can think of this from the perspective of each agent as a contextual MVP, where you provide the context. And so what happens is our agents can really change their behavior based on the values of alpha. So for example, if we vary the center bias, we can force the agent to move from one lane to a different lane. If we vary how urgently we want to get to goal, we can sometimes see our agent taking longer routes to get to its goal if it thinks that that longer route might seem safer. And so we can see all sorts of really rich behavior emerge just by varying these alpha weights. We also, generate diversity by conditioning the size and the goal of the agent. So our agents are all different shapes and sizes. Some of them represent cyclists, some of them represent pedestrians, some of them represent bicyclists, but it's all one neural network. But we provide the size, like the width and length, as an input to our neural network. And based on those values, the behavior changes. So over here on the bottom left, we have our goal, and there's an obstacle in gray that's preventing us from getting to our goal. When we're this thin green car, we know that we squeeze through the obstacle, and so the car just drives right through and goes to its goal. But if you're this thicker blue car, you can't squeeze through the obstacle. And the car will immediately do a 3-point turn and use it to go around. And if we're this really like small purple square, we have a really tight turning radius. And so instead of doing a 3-point turn, we just execute a U-turn and go around. And we'll see our cars really change the routes and behaviors that they take based on their size. And if you become really small, you know that you're a pedestrian and you know you're allowed to cross the edges of the road. So putting this all together and doing all this training in this diverse world and training for 1.6 billion kilometers, we get our Gigaflow policy. And what's really kind of surprising and exciting about the Gigaflow policy that comes out is how well it generalizes. So there are 3 benchmarks that we test the Gigaflow policy on. The first benchmark is called Carla. Carla is a photorealistic simulator where people have designed these benchmarks that consist of very long drives, like 20-plus-minute drives, where every other agent in the scene is a kind of hand-scripted actor that some human has written down. So they're not human policies at all. There's some kind of scripted policy that some engineer has designed. They kind of drive a little human-like, but not exactly. And in this simulator, we set the state-of-the-art score. So this benchmark has a kind of scoring system. We set a state-of-the-art score of 94.7 without ever training in the simulator or ever seeing any data from the simulator. So we beat the state-of-the-art by a lot. And one caveat that is important to note if you're not familiar with Carla is the top score is 100. But a score of 100 isn't actually necessarily achievable. For example, one thing we get frequently dinged for is that we'll be stopped at a stoplight, and then one of the scripted pedestrians will just run into the side of our car. Not a lot we can do about that. But we set kind of a state-of-the-art score there without any training. So this is with kind of hand-designed human actors. What happens when we use human data? Well, there's a benchmark called New Plan, And what New Plan consists of is drives in Boston, Vegas, and Singapore with human replay. So somebody collected a bunch of data of humans driving around these cities. And the way the benchmark works is all the cars but one are just replays of these trajectories. They're just like driving along and replaying the trajectory that was recorded. And then one of the cars is your car, and you have to drive through those replay trajectories without colliding with them and getting to your goal and stopping at stoplights and all that. And here as well, we set kind of a state-of-the-art score without ever seeing any human data or ever training on this benchmark. This benchmark is somewhat saturated in some ways, so there's not a huge difference between our performance and the performance of prior benchmarks. But what's cool about our result here is that when we watch the videos, there are in total 15 collisions in the data set, in our results on this data set. Of those collisions, 9 are a pedestrian running into the side of our car while we're stopped. 4 are kind of benchmark failure, where a car is teleported on top of us, which again, we can't really do much about. And then 2 are contestable. So we think they're not our fault, but we'll release some videos at some point and people can contest that. So SOTA here as well. And then on a kind of similar benchmark that we constructed for Waymo data, we also kind of get a sort of state-of-the-art score relative to Waymo specific things. And we can see that all this extra training time is really like necessary. So on the bottom here, we've plotted how we do as a function of the amount of millions of kilometers we've driven. And little trophies, this is when we hit state-of-the-art performance on these benchmarks. So by 800 million kilometers, we are state-of-the-art on all 3. And our performance saturates somewhere out at 1.4 million kilometers on all the benchmarks. Billion kilometers. So I'm going to pause here for so across synthetic benchmarks, so benchmarks with hand-designed actors, and across benchmarks that containing human data, we are zero-shot state-of-the-art. So we see map generalization to held-out driver policies, and an extreme level of robustness. So I'm going to pause here for questions because I've just been kind of rambling on for a while. So if anyone has any, this might be a good moment to ask.
So
Yeah, I just had a clarifying question.
Yes.
When you were mentioning different rewards, how does that vary during the training? So you keep changing the reward function while a single policy is being trained, or is that also a parameter that's provided in the input somehow?
Yeah, great question. So every time an agent is spawned into the world, we draw a new sample for the weights of that reward function. So every agent, like we're constantly respawning new values of that reward function, and probably no agent in the scene has the same reward function at any given time.
Yes, but in the end, is there just one policy that's trained, or are there
Yes,
different?
we're just training a single policy, a single reward conditioned policy.
Okay. And in the spawned agent, maybe there's something I didn't quite understand, because in the spawned agent, when you generate the game, isn't the policy remain the same during one rollout, or?
Yeah, the policy remains the same, but because it's conditioned on the reward function, it changes its behavior to optimize whatever reward function it's currently playing.
Oh, the policy has as part of its input the reward function.
Exactly. It knows the reward function is part of its input, and its size and its width is also part of its input.
I see. Okay.
Great question. Thanks for the clarification.
yes,
I think
Sean.
that.
Yeah. So I'm maybe following up on the previous point. When you actually evaluate the final policy, what conditioning do you use for the rewards?
Yeah, so here we kind of just set all the rewards to like a value that we think looks like safe behavior. So we kind of take all the components that seem like riskiness and we turn them down, and we set all the components that are like normal law following to kind of maximize law following.
Okay, so you like hand choose the final weights for conditioning the last, like evaluated policy basically.
Yes, but we do not change it per benchmark. It's the same conditioning for every benchmark.
Okay, do you think there would be a way to like automatically choose what that policy would look like, or is that still something where either human data or like hand tuning is required?
I think that it kind of depends. So if you wanted to maximize human likeness, right, you maybe would use a little bit of human data to pick the values of that. And you could imagine picking it online, just like, based on like, other metrics such as like closeness to human drivers, deviation from kind of expected trajectories, that type of thing. So, but we don't do that, but I think it's a cool idea. Is there another question?
Yes.
I think I heard a ping.
Samir.
Yeah, thank you. I wanted to ask, using reinforcement learning in developing the model, wouldn't using an LLM or VLM in it would be an improvement for this? The perfect size or parameters will be, instead of reinforcement learning, deliver better results?
Well, it really depends, right? So, is an LLM calibrated to generate motion and reason about other agents? Not really. It can give you reasonable initial suggestions, but at some point you want to acquire a lot of experience, and running this through an LLM really would slow you down in a lot of ways. I think there's a lot of interesting things you can do with an LLM to make the rate of progress, to like cut down the number of samples that you need. But I don't think, it's the only thing that's needed here.
Okay, thank you.
Right. Yeah.
Okay.
Yes, Meher.
Okay, so we got a couple questions. Sorry, is there a question?
Hello. Hi. Yes. You mentioned. I'm sorry if I missed this, but you mentioned that you're using the Carla simulator, right?
We do use the Carla simulator for a few things. Yes.
So I was wondering that how this. I'm not familiar with this simulator very good, but how does this generalize to the real world? Because I'm thinking that the policy that you learn in the end is going to be bounded by this, but how much this simulator is going to generalize to the real world, right?
Right.
So there are some cases that you might see, for example, a Tesla might see in the night that, I don't know, a deer comes in front of it. Some of the data that Tesla might see in the real world, but it might not be in the simulator.
Sure. Okay.
Right.
So here's the idea. So our simulator assumes the world consists of bounding boxes, and that it's really important not to collide with any bounding box. If you have a good perception system and it converts things into bounding boxes, like even a deer, right? Your perception system says, here's a deer, here's a bounding box running across the road, don't collide with it. The subsequent agent that we learn from that is going to try very hard not to collide with that deer. It doesn't know what a deer is, but it knows that it should not collide with bounding boxes. Now, you could ask a question about whether this is a lossy representation of the world, whether it's reasonable to map the world into drivable space and bounding boxes. And there may be very complicated regions you can come up with where that's not the case. For example, if there is someone on the other side of a car, you might see their shadow. And so you might reason from their shadow to the fact that there's somebody on the other side of your car, and you should maybe slow down. But this kind of bounding box representation and drivable space representation captures a lot of the complexity of real world driving, including deer.
Yeah. So do you think that this simulator is a good simulation of the real world driving, right?
I think that representing the world as a set of bounding boxes that you shouldn't run into and a set of space that is acceptable and a set of space that is not acceptable to drive on is a pretty good representation.
Yeah. Okay. Thank you.
Did we test the policy on the real world? We have not put the policy in a car yet. That's something that my lab is like actively trying to do.
Sudipta?
Yeah. Hello, can you hear me?
Yep.
Yeah. I'm curious about have you explored, or is there like work in the literature that is exploring how to extend these approaches to the situation where the perception system is not perfect, and you start corrupting your data and see if you can still learn robust policies? Can you comment a little bit on that?
Yeah. So the first thing I'll say, and I didn't mention this, is we actually corrupt the data a lot during simulation. We drop out a lot of perception. So there's a lot of perceptual noise in our simulator. But you can also learn a model of perceptual imperfection and just stick that into the simulator as well. And so there's a lot of ways to put these
do a lot of
together.
dropouts, or do you have like systematic noise? Because if you start putting in systematic noise, does it mean that the policy you learn will automatically learn some uncertainty model?
Yeah, so we don't touch uncertainty modeling here, but yes, if you added systematic noise, the policy would, and that's something we're working on in future work is putting this thing together. But I also don't think it's going to be super hard. Like, I don't think the actual hard thing in driving is like perceptual uncertainty. But you know, one could disagree about that.
Yeah. Okay. Thank you. Great talk.
My headphones. All right. So just to kind of get into it, so we can also see that, and I'm sad that I don't have any videos here, but these policies solve challenging out of distribution scenes. So over here we have a bunch of cars queued up behind this obstacle, these red dots. I can't drive through them, and they all have a goal on the other side. And at the beginning of training, they're totally unable to do it. And by the end of training, having colored agents in green, if they succeed, they'll get through this every single time without a collision over thousands and thousands of rollouts. Like if I could show the video, they kind of negotiate with each other to see who gets to go. We also see that they learn long horizon decision making, which is a really hard thing to do in reality. So over here we have a vehicle, it wants to get to its green goal, and there's an obstacle on the shortest route. And to go through that obstacle, get around that obstacle, you have to drive into the oncoming lane. And what we see in this bottom plot is that our value function here, we're like plotting in dark, like negative states that the value function says are really bad. It says going near that obstacle is an extremely bad idea, even though it's 150 meters away. And if you're shorter horizon than that, what you'll see policies do is they'll drive up to the obstacle, then they'll realize it's a bad idea, then they'll turn around, and then they'll reroute themselves. Whereas our policy immediately routes itself to take the longer route that does not have to drive into the oncoming lane. It's quite hard to get this level of long horizon decision making. Some quick observations since we're starting to run low on time. First of all, this planning policy is tiny. It is 3 million parameters. I did not think that you could get this level of robustness into a 3 million parameter neural network. I kept trying to make it bigger, didn't really help. And it also implies that kind of if you scale things up, you can actually push a lot of stuff into a small neural network. It also implies that maybe planning is not as hard of a problem as we thought it was. You know, maybe you'd think you'd need a much bigger neural network to do it. 2, you can fit many policies into one net. This single neural network represents pedestrians, cyclists, drivers, cautious drivers, risky drivers, law-obeying, not law-obeying drivers. It's all just by conditioning it. We get all of these different behaviors out of this one neural network. And it suggests that maybe you can actually distill a lot into a small MLP. 2, 3, there is no wall. So in self-play, when we condition the weights correctly, we can actually generate 1 million kilometers between collisions, which is an incredible level of robustness for an end-to-end policy. You know, I kind of kept thinking it wouldn't work, and it kind of does. There we have, for 9 nines of transition-free, collision-free transitions. I'm kind of can ignore this plot; it's not super important. So, to maybe summarize and try to give some concrete takeaways that are applicable in domains besides driving, I think what we've built here is what looks like a rough pipeline for robust multi-agent autonomy. So the Gigaflow system is something like this. It's a goal-reaching game. So we're throwing agents in the world and asking them all to reach their goals. Some kind of reward randomization to generate diversity, and then a scalable algorithm for using those trillion steps of experience. But if we abstract this, we might think of this as some highly interactive task, some way of generating diversity for your partners, and then some scalable RL algorithm. And you could put a lot of things into this pipeline. You could put in, for example, collaborative information discovery, trying to find to work together to like search through Wikipedia more efficiently. You could use weak and strong LLMs as your diverse partners. And then of course you scale up RL as your thing. Or if you're thinking about robotics, you might think about human-robot task handoff of objects as like this huge set of games that you could play. You could, again, use randomized reward preferences, like pass me the left hand versus the right hand or things like that. And then again, scale up RL. And so I think that there's a lot of things that are going to fit into this box and that can be used to generate autonomous systems that are kind of zero-shot compatible with humans or that work together as a really capable team. So quick takeaways. We've built the first simulated planner that zero-shot ACEs benchmarks. And we've shown that there's not really a wall for end-to-end RL. It just kind of fits into the same scaling box that a lot of other things have fallen into. And maybe we've put across this idea of this like large-scale, open-ended world in which we kind of do self-play as a type of pre-training that builds capable skills that can be reused elsewhere. So you might spend some time asking yourself, what other diverse, rich worlds can we build, and what skills will emerge from that? We're low on, actually, a couple quick limitations. First of all, our policy isn't particularly human-like. It tends to drive a little bit slower than a human, and that means that when we place it on benchmarks of human likeness, we're like 30th or 40th or something like that. We're super robust, but we just like don't really drive as fast as humans want to. I'm going to skip this one, actually. Two, there is some reward design going on here. We have a lot of different reward components that we use to randomize over. But none of these reward functions specify how the agents should interact with each other. They specify laws and conventions, but they don't say like, hey, keep some distance from the agent, yield here, don't yield here, that type of thing. So the agents are learning to interact with each other, but in a world where we have laws and conventions. So what's next? First of all, we've been working on building an open source reproduction of the simulator. My students have built a simulator called GPU Drive that converts from C++ to CUDA. So you write C++ code, you get a like parallelized CUDA simulator out of it, which is nice because writing this first simulator involved a lot of complicated PyTorch tensor puzzles that are extremely fun, but also somewhat limiting. We currently have an open source policy that is collision free in 99.1% of the rollouts, and we're continuing to accumulate extra nines in the hope of open sourcing a policy as robust as the one in this paper. And 4, we've been working on relaxing some of these assumptions about not using any human data and trying to figure out, can we make our policies both extremely robust and human-like by incorporating just a little bit of human data. And so we have some papers out on both of these that you can take a look at if you're interested. And I'm just going to get to the end, some quick acknowledgements. Marco, David, Alex, Brody, Alexei, and Eric are equal co-authors on this paper. And then Taylor, Stuart, Ozan, Philip, and Vladlen for leadership. For this open source simulator, Sam Kazimkani, Ara Pandya, Kevin Joseph, and Daphne Cornelise, and Brendan Chocolate helped build it. And I want to end by thanking my lab members who are all lovely and contributed to bits of this talk here and there. And take any questions that we have. I unfortunately need to leave almost on the dot, so I don't have much time for questions. So I'm going to leave shortly after this. But thank you so much for taking the time to listen to me in your afternoon. Yeah.
Thanks for joining us. It's really a really great presentation.
Yeah, thank you guys so much for having me. This was really fun.
Me too.
And if you have additional questions, just shoot me an email. I'm always happy to talk more. This is, work that we're all really excited about, and always happy to chat more about it.